Jeez. All right, so let's take a look. Brianna? And we need to make a test time today, right? Don't walk out of here without reminding me that. I've already forgotten it. Benaya, yes, good. Ka, you back there? How are you doing, man? And Landon. All right. You work last night? Yeah. Called off yesterday. Good, good. You all caught up? Michaela. You out there, Michaela? No. Sydney is. All right, cool. 1, 2, 3. This is the biggest class like ratio to virtual. Most of you guys are actually in here. Cool. How was lunch yesterday? Was it weird? Brianna, you haven't been here in a while. Is it different? Cool. Yeah. But you had lunch, right? Yeah, you met it for lunch. So what did you think, like seeing the cafeteria, or are you in some different room now? Yeah, it's the same. I thought it would be more people in there though. I figured it would look different. What do you think, Ka? It sounded like they were picking on you. I assume that there's more people sitting outside than just you. But there's other people besides just you. They're not like, Ka, you're gonna go out there and eat because you're sloppy or anything, or what? Yeah. What did you get, the pork tenderloin sandwich? Is that what it was yesterday? It was nasty. So those of you at home, the food for lunch is still nasty, according to Ka. Anybody like the food? No, apparently nobody. Yeah, right? Your lunches at home might be better than what they're getting here. Unless, are they still doing like you pick up your lunches? You can do that? Unless you're doing that, maybe. I don't know what they give you though on that. I have no clue. All right. So let's handle the business of last night's homework, which is due Thursday, which is tomorrow. Any questions on reading? Is this okay? Any questions on this guy right here? Looks a little blurry, little bluzzy. Oh, too much. So let's take a look. I won't do it for 95 degrees because I want to give you guys the maximum points I can on this. What is the solubility for 95 degrees? If you recall, let's do it for sodium chloride at 30 degrees. So you need to find the curve that is sodium chloride. You find 30 degrees, you go up to it. So there it is. That looks about like 38 to me, 37, 38, right? You go over here. That means that in 100 grams of water, we can put, in 100 grams of water, we can put 38 grams of sodium chloride at a temperature of 30 degrees. That's what that means. What is the most soluble at 18 degrees? Well, let's do the most soluble at 10 degrees. Here's 10 degrees. Who is the most soluble at 10 degrees? Well, the one with the highest line. Right there, Ki. Now let me ask you this. Let's say we're talking about a solution of let's do KNO3, of KNO3. If I am able to dissolve 110 grams of KNO3 at 50 degrees temperature, that plot would be right here. That is way more than I should be able to dissolve of KNO3 into that water. What does that mean? That KNO3 then is what? Saturated, unsaturated, or supersaturated? Supersaturated. I've got more than I should be able to have. If it's on the line, then that's the saturation point. That's how much you should. That's the max. Let's say I dissolve 20 grams of KNO3 at 40 degrees. That means I could dissolve a lot more KNO3, and that would be unsaturated. And here's the cool thing. Let's say I have at 60 degrees KNO3. I should be able to dissolve 105 grams of KNO3. Let's say I drop this down to 30 degrees. 30 degrees, KNO3 is right here. That is about 48. So if I had it up here and I had 105 grams dissolved in it, and then I cool it down, I can only dissolve 48 grams. 105 minus 48.
It's 57.
So that means that 105 minus 48 is 57 grams. 57 grams would form on the bottom in a layer of KNO3. You might have done this if you've ever made like Kool-Aid with room temperature water, and then you put it in the refrigerator. As that cools, all that sugar that can't be dissolved in there, because you're over the max, as it cools, will form a layer on the bottom. That's what happens. So these 15 questions are due tomorrow. Please make sure you get those done. And the rest of the day, we are going to talk about molarity. Molarity. All right. So molarity is what chemists use as a concentration. What is a concentration? Well, concentration tells us how much of something is in something else. A lot of times concentrations are already figured out for you. All you've got to do is a little bit of measuring. For example, a Tide Pod, that's concentrated. When you toss that Tide Pod into the washing machine, that's exactly the amount of concentration of soap you should use for a full load. It's already measured out for you. If you don't have Tide Pods, then you have to measure it out. And what is it usually? Well, if you have liquid soap, then it's usually the lid, right? The cap. You sit there and press the button or pour it into the cap and dump that into there. Again, that concentration, they've already measured the measuring cup for you. It's that cap, right? What's that? You just pour it in there. So you might, your concentration may be too high sometimes and too low other times, right? They've made it so that whenever you pour that into there, that's the actual concentration for the best clean. So yours may be too high or too low sometimes. I mean, I get you. If you use powder, so the powdered stuff, that right there, you have a scoop that tells you how much of that to use, right? If you've ever seen the powder. That maybe you don't have powder for your laundry, but you have powder for your dishwasher. Same thing, there's some type of little measuring device and you put the powder in there until it reaches that. And that's the concentration that you should use. How many of you have ever made orange juice from the frozen log? Yeah, right? They tell you how much water to put into that. Or lemonade from the frozen log. They tell you how much water to put into that. That's because the frozen log is what we call concentrated. So we need to add water to it. Does anybody know what that means when we add more solvent? This is a term for that. We make something less concentrated by adding more solvent. Starts with a D. Ka? You know? No? Dilution. We dilute the concentrated solution by adding more solvent. We make it weaker in concentration. We made it diluted, right? there's a lot of different ways to look at concentrations. For example, spirits and liquor, they had something called proof. If something is 100 proof, it can actually light on fire. So if you're at 100 proof, that's 50% alcohol. It has to be 100 proof in order to light on fire. Basically, you take the proof and you divide it by half, and that tells you how much percent alcohol by volume it is. Most spirits are 80 proof. Like vodka, for example, is 40% alcohol by volume. If you don't know these words, that's fine. Basically, I'm just telling you the concentration system they have for it. The vodka is 80%, I'm sorry, 80 proof, which is 40% alcohol by volume. Wine is usually not called proof because the proof is to not light it on fire in a sense. That gives you proof of the alcohol's potency. Wine is usually measured in percent alcohol by volume. They don't bother with proof, but wine is usually between 8 and 12% alcohol by volume. Beer is usually 4 to 6% alcohol by volume. What's that? Yeah, like your pilsners and your lagers. So what you probably learned in your health class is that one beer at 5%, we'll just put 5%, it's between 4 and 6 usually. You can have 12 ounces of that. An average adult body can have 12 ounces of that. With wine, being double that at between 8 and 12, you should only have a 6-ounce glass of wine, right? 6 to 8 ounce glass of wine. This can be 12 to 16. And then a spirit, you should only have 2 ounces because they are 40% alcohol by volume. So you can see your health teacher may have given you this very quick run over that 1 beer per hour, 1 glass of wine per hour, or 1 shot per hour will help you maintain below a 1.0 blood alcohol level, which in our state, it's actually 0.08 blood alcohol level that you would be allowed to get. So these concentrations allow us to determine how much of each of these a person could feasibly drink if they were drinking what they call responsibly, right? But that's the idea behind it. All of these different percentages means that the different amounts of alcohol in each of these is different. So the volumes that should be consumed are different. We, as scientists and chemists, we use what's called molarity. And we'll get to why we use molarity eventually, but to start it off, this brings us back to what we call the moles. The moles of solute divided by the liters of solution. If you know these two things, then you can find molarity. So it says calculate the molarity of a solution made by adding 141.7 grams of nitric acid, HNO3, to enough water to make 750 milliliters of solution. So we need 141.7 grams. We need to get that to moles. And we need 750 milliliters, and we need to get that to liters. Now, the way that I taught all of my classes last semester was using dimensional analysis. So our final want is molarity, so that's moles per liter. So out of these two things, we have to put something on top to get us moles. The easiest one is 141.7 grams. We need something on bottom to get from to liters. In this case, 750 milliliters. So we know, hopefully, you have this memorized. Every 1,000 milliliters is 1 liter. Take the milliliters and the milliliters, and they will cancel out. That's how I knew I needed to put that milliliters on top. Now I've got liters, and now I'm done with that portion. Now I just got to change grams to moles. In order to change grams to moles, we need the periodic table of elements. we're dealing with HNO3. H is 1.01 on the periodic table of elements. Nitrogen is 14.01. And oxygen is 16. But the oxygen we're going to have to multiply by 3. 3 times 16, that's 48. So we're going to add all these up. 1.01 plus 14.01 plus 48.0.
The answer is 63.02.
So we get 63.02. That's grams per mole. What am I going to put on bottom? 1 mole or 63.02 grams? Yeah, the 63.02 grams, because I want the grams to do what? Cancel out, and that's equal to 1 mole. 141.7 divided by 750 divided by 63.02 times 1,000.
That would be about 2.9979.
3.00 moles per liter. Actually, I'm sorry, 2.998, because significant digits, we need 4 of them. .998 moles per liter. Another way to write this is 2.998 big M. Usually you'll see a line under it. The way we say that is 2.998 molar. And that's how we find molarity. If you did not learn dimensional analysis last semester, this is the easiest way to do it. If you did not get it down, you obviously could do this in separate steps and find the moles, find the liters, and then divide the two. There's a lot more thinking to do in that, and a lot more like error from rounding twice. You can see that they're off 0.001 because of rounding. But let's take a look at example exercise number 1. This is calculating the molarity of a solution made by adding 2.42 grams of rubidium to enough water to make 250 milliliters of solution. So again, we want molarity, so we put moles over liters up here. Out of these two, 2.42 grams or 250 milliliters, which one can get me moles? 2.42 grams. So I'm going to put that on top. And to get liters, I'm going to use the 250 milliliters. And some of you are able to do this in your head, and you're just like, okay, that's the same as 0.25 liters. So you could just change that to 0.25 liters in your head if you're able to do that. Basically, there are 1,000 milliliters in a liter. So you're more than welcome to do that. I'm not going to teach you how to do your math. But there we go. That's going to do the same thing. That's going to get that milliliters to liters. I knew to put the milliliters up top so that they would cancel out. Last thing I need to do is just simply divide this by the molar mass to get the moles. So every so many grams is 1 mole of the substance. I got rubidium and chlorine. Rubidium is 85.47. Chlorine is 35.45. 85.47 plus 35.45.
The answer is 120.92.
So that's 120.92. Every 120.92 grams is 1 mole. If it's on top, I multiply. If it's on bottom, I divide. 2.42 divided by 250 times 1,000 divided by 120.92.
The answer is about 0.08005.
2 significant digits. So that is 0.080 moles per liter, or I could rewrite that as that right there. Either one works. It's calculating molarity. And what if instead of grams, they gave me moles? Well, then I would just take moles and divide it by the milliliters. What if they gave me liters too? Well, moles divided by liters is going to be molarity, so I would just do that. You really got to look at what you start with and what you want to end up with in the end. If they said, hey, there's 4.0 moles in every 2 liters of this, then we got 4 divided by 2, which is 2 moles per liter. I didn't have to do all this other stuff because I was given moles and I was given liters. Easy enough. All right, a chemist wished to prepare 0.500 liters of an 8 molar aqueous solution of sodium hydroxide. How many grams of sodium hydroxide should she use? So right here, I want grams of sodium hydroxide, so I'm going to put that out here at the end. Before I wanted moles per liter, I wanted molarity. This time I only want grams. So let's ask this question. Moles per liter has how many different units? Moles per liter versus gram. How many units does grams have? When I say units, how many words are there? Gram. 1, right? How many units is moles per liter? 2, moles and liters. I only have 1 unit here. So that means I want to start this whole thing with 1 unit. Up here, I was trying to find moles per liter. So I needed 2 units, grams per milliliter. The thing. Here, I want grams. So I want to start with 1 thing. 0.500 liters or 8 moles per liter. 0.500 liters or 8 moles per liter. So I want to start with liters, just liters, because it's 1 unit, 0.500 liters. Now take a look at this, 8.0 moles for every 1 liter. That's going to go on bottom. 1 liter down, 8.0 moles. I have moles now. I want grams. Well, I can convert from moles to grams by looking at the periodic table. 22.99 plus 1.01 plus 16.
The answer is 40.
So that means that every 1 mole goes on bottom, so it cancels out, is 40 grams, 40.00 grams. 0.5 times 8 times 40.
It's 160.
So that's 160 grams of NaOH that I need. Again, I had 1 unit to start with because I want 1 unit to end up with. Totally different than here. I wanted to start with 2 because I needed moles per liter. And what I'd like for you to do is take a second to complete exercise 2 and see what the chemist is going to do to get that. Complete exercise 2 real quick. While you do. All righty then. The chemist wishes to prepare 275 milliliters of a 2 molar aqueous solution of sodium hydroxide, how many grams should he use? We want grams, so we're going to start with grams. Out of these two, which one has 1 unit? Louder? Nope, 2.0 has moles per liter. Yeah, so the milliliters. 275 milliliters. Every 1,000 milliliters is 1 liter. That causes milliliters to cancel out. Now I have liters. This is 2.00 moles for every 1 liter. So every 1 liter is 2.00 moles, and every 1 mole is 40.00 grams. $275 divided by 1,000 times 2 times 40.
It's 22.0.
0.0. Another way we could have done this is we could have sit there and said, okay, I'm going to just change this milliliters to liters. And we could have started there. Then we would have just said, okay, every 1 liter is 2.00 moles. And every 1 mole is 40 grams. Totally up to you on that. It's the same exact thing. It's just one takes more thinking in your head. For tomorrow, in addition, you should practice 1, 2, 3, and 4. Basically, in each of these, you are solving for molarity. So that means 2 units. That's what you should do before the end of the period today. We'll check the answers to this tomorrow. Then we'll take a look at making a dilution. And then maybe we'll have a laboratory on Friday. I'm hoping. We'll have to wait and see, though. It's hard because the AP kids are baking buffers, but we'll see. That's what I got for today. If you've got questions, by all means, come and stay in the breakout. Stay in the Zoom, and we